Welcome back. In this video, we're going to wrap up our discussion of Newton's laws with air friction. We thought that we would wrap this up last time, but it turned out that I wanted to break this video up into two parts. So we're going to have basically the same essential question as before. We're looking at the nature of frictional forces, in this case, fluid friction. Okay, so drag forces, or fluid friction, they slow an object down as they pass through the fluid, and they act in a direction opposite to the velocity. They're actually functions of the velocity, so the force is a function of the velocity, and they impose what we call a terminal velocity, Vt, which is reached when the acceleration becomes zero. Now, usually we talk about drag forces as a function of velocity, so Fd of v has two terms to it, bv and cv squared. And these constants, b and c, depend on the shape and size of the object and the properties of the fluid. And what we can see here is that one is a so-called linear drag term, because it just has v to the 1, and the other one is quadratic. So we're going to end up deriving linear drag, and we're just going to look briefly at quadratic, but you don't see that as often in physics C. So B is important at low velocities, and C is important at high velocities. For example, let's think about the drag force in free fall. You start with an object that has the force of gravity mg, and this is assuming that V initial is 0. Then, after a short period of time, it's going to be moving with a certain speed, and since the drag depends on the velocity, when it's at a low velocity, we have a low amount of drag. But then, as time goes on, this drag force is going to increase in magnitude. Eventually, the drag force Fd is going to equal mg, and we will say that we achieve terminal velocity because the net force is 0, and therefore the acceleration is 0. And at this point, the drag force is actually equal to mg. So in free fall, in general, we say that F drag is equal to bv plus cv squared. So when objects are moving slowly, we use this form of bv, and sometimes you'll see it as kv. Most of the time that's a b though. And for fast-moving objects, you have a slightly different equation where C depends on a drag coefficient, a density of the fluid, and the physical size of the object, so the cross-sectional area. So quadratic drag is much more complicated than linear drag. So let's show that for slow-moving objects, when the drag force is equal to bv, let's show that terminal velocity is equal to mg minus b. So we can assume that downwards is positive to make our life easier, and then we can just say that Fnet is equal to ma. Now Fnet is going to be mg downwards minus the drag force going upwards, and that's going to be equal to ma. And I'm going to cross this out because we want terminal velocity here, and terminal velocity will be achieved when the acceleration is 0. So that's going to go away, but I want to introduce another way of writing this acceleration. We can write it as dv dt, because that's just a definition. Okay, so that's still going away and becoming 0, but that'll be important coming up. So then we set this equal to 0, and you can see from this we bring mg to the other side and divide by b, and that's what we wanted to do. Okay, well now let's actually derive this, and let's show that the speed as a function of time has the following exponential format. And first of all, let's graph this and try to understand. Okay, let's put v here and t here, and let's say that downwards is positive, so that means that this is actually the downwards direction. Okay? And we're going to max out at Vt. And Vt is going to be given by this mg over b that we talked about. That's Vt. But then we're going to have 1 minus e to the minus bt over m, which qualitatively means that we increase and then reach an asymptote. Okay? Because as t goes to infinity, e to the minus t is going to basically go to 0. So that means that v will approach vt. Also, we should point out that when t is equal to 0, e to the 0 is 1, so v is equal to 0 to begin with. So that's just looking at our graph qualitatively. Okay, so how do we get this? Well, we're going to start with Newton's second law. So F net is equal to ma. And now we're going to write mg minus bv. And we're going to write that this is equal to m dv dt. So this is what we talked about in the last slide. Okay? So what we're trying to do is to solve this equation as a function of v. We want to solve this for v of t. And that's really what this v is right here. Okay? This is complicated by the fact that we have the variable, but we also have its derivative. Okay? So this is what we call a differential equation. Now this is a very easy one to solve. Okay? But it turns out that there are some tricks to doing this. And the first trick is that we want to divide through by b, so that we have mg over b minus v equals m over b dv dt. And that's a trick that we can do because we know that mg over b is a special number. It's the terminal velocity. And as a matter of fact, I can replace that and say vt minus v equals m over b dv dt. Okay, now at this point, this is what we would call a separable differential equation. And you're not supposed to know a lot about differential equations for AP Physics. And if you're just taking calculus now, this might be really early in your calculus class to be solving this kind of a problem. So I'm going to walk you through it. And the idea is that we want to separate all the v's and the dv's and put them on one side and put all the t's and the dt's on the other. Well, we don't have any t's, but we do have a dt. And so if you imagine that this whole thing, vt minus v, is being multiplied by 1, then we can just actually move it to the right side and move m over b to the left side along with dt. So this would be like this. dt is here, and then we have b over m, and that would be equal to 1 over vt minus v times dv. Okay, so far so good, everyone? Now, in order to integrate this, we're going to have to integrate, and I'll write this part a little bit larger. We're going to integrate over a different variable, t prime, so that we can integrate from 0 to time t. Then over here, we're actually going to integrate dv prime, oops, and that's going to be over vt minus v prime. And this is so that we can integrate this from 0 to v. Okay? Now, even if you don't understand a lot of the math that follows, getting this far in setting up the problem is very important. And getting this far, like on an AP question, will often get you some pretty hefty partial credit. Okay? So at this point, you might see that on the left side that I have b over m dt prime, and that's just going to integrate to give us b over m times t prime evaluated from 0 to t. Now on the right side, it's a little bit more complicated. And this is a special integral, but basically anytime you have 1 over x, you need to write that integral as the natural log. Okay, so the integral of 1 over vt minus v prime is actually the natural log of vt minus v prime. And we have to evaluate that from 0 to v. But before we do this, we have to think about this. It turns out that when you take the derivative of the natural log, it turns into 1 over x, which makes sense. And I'm not going to go into the details of that right now, but we do need to put a negative sign here so that when we take the derivative, things will work out. So now let's continue, and we'll come up to here. So b over m times t prime evaluated from 0 to t is just going to be b over m times t. But this negative sign here I can bring to the other side and put it on this, so that on the right side I'm just going to have the natural log of vt minus v prime evaluated from v to 0. Now to do that, we plug in when v prime is equal to v, and we would then subtract when v prime is equal to 0. But with natural logs, when you subtract, you can just divide like this. Okay, now remember our goal is we need to write v. We want v equals. So the next thing we need to do is to exponentiate each side, which is going to eliminate the natural log, and it'll give me e to the minus b over m times t on the other side. You can see that things are starting to fall into place because I have e to the minus bt over m in my equation. So I'm going to switch the order in which I write these. So vt minus v over vt is equal to e to the minus b over m times t. And now you can see why I've written everything in terms of vt. Otherwise, I would have a whole ton of mg over b's floating around, and that would just make it messier. So vt minus v is vt e to the minus b over m times t. And we bring that to the other side and switch our negative signs, and it looks kind of like this. And finally, we can factor out a vt to write 1 minus e to the negative b over m times t. So that's it. That is our velocity as a function of time for linear drag. And as we talked about before, it fits our qualitative description of what's happening to an object. Now, the other reason why I wanted to introduce this is that we're going to see this math later on in the course. When we do RC circuits, we're going to see that current as a function of time is going to behave exactly like the acceleration, and the charge as a function of time will be exactly like the velocity. So this is math that is going to come back when we do RC circuits if you stick with us for the second half of the course. Okay, now you can also have quadratic drag, and we're going to show first of all that terminal velocity for quadratic drag is equal to this expression. And this is pretty easy. We know that the acceleration is 0, so these forces are equal. So mg is just equal to 1/2 d rho a v squared, and that's v terminal. So v terminal is going to be 2 mg over d rho a square root. Okay, so that's not too tough. Now the tough part is this last one. Derive an expression for the velocity of the object as a function of time. And we are going to nope our way out of this because this is going to involve some crazy math. I'm going to give you the answer, but you're typically not going to see this on an AP problem. It's going to be VT times the hyperbolic tangent of GT over VT. Now, what the heck is a hyperbolic tangent? Well, the hyperbolic tangent of alpha, and in this case, GT over VT is alpha, is equal to e to the 2 alpha minus 1 over e to the 2 alpha plus 1. So again, the exponential behavior is showing up. It's just a lot more complicated mathematically. And this math is a bit beyond the scope of this course, and also it's beyond what AP expects you to do. But if anything, you should understand how to find the terminal velocity for linear and quadratic drag. Okay, so next time we're going to start talking about work and energy and how to use force to analyze systems in terms of the energy in those systems.